Hello everyone, today I'm going to be talking to you about the project that I've been working on in Dr. John Labadia's lab in the Institute of Healthy Aging, which is establishing how the mitochondria-to-HSF1 stress response influences age-related pathologies across tissues. So the importance of our work and the reason why we're conducting this research is because in 2050 more than 1 in 5 people will be over the ages of 60. And there is a strong link between aging and an increase in diseases. For example, heart disease, cancers, diabetes, neurodegenerative diseases. In this graph, it shows here that the number of percentage of patients with at least one disease increases with age. This has a massive impact on social and economic strain on individuals, families and communities. Thus showing it is incredibly important we find new ways to promote healthy aging across society. Aging is associated with a whole range of molecular and physiological changes. In order to improve healthy aging, we must better understand the processes behind it. Lopez et al. In 2013 enumerated 9 tentative hallmarks that represent common denominators of aging in different organisms. One major aspect of aging and an area of particular importance is the loss of protein homeostasis or proteostasis. This is associated with a wide range of age-related diseases, for example, macular degeneration, type 2 diabetes, and Alzheimer's disease. So what is proteostasis? Proteostasis is the regulation of functional, balanced proteome via molecular chaperones, autophagy, and the proteasome. However, when it goes wrong, it leads to protein aggregation, tissue dysfunction, and disease. So research is really looking into different pathways to maintain this proteostasis network. It has been recently discovered that reduced electron transport chain activity extends lifespan. One way it does this is by maintaining proteostasis through the increased activity of the transcription factor called HSF1. But it is unclear how the mitochondrial stress and activation of the mitochondria-to-HSF1 stress resistance pathway influences the health of specific tissues. So this leads us into our questions. Firstly, we want to see how does reduced electron transport chain activity affect the onset and progression of age-related pathologies in tissues? And which tissues does the mitochondria-to-HSF1 stress response pathway operate in to extend lifespan and enhance stress resistance to promote proteostasis? To address these questions, we use 2 approaches to reduce mitochondrial function. We use coccyx-C RNAi and electron transport chain mutant ISF1-CTV1. So firstly, we use coccyx-C RNAi, which is the terminal enzyme of the mitochondrial respiratory chain in complex 4, as shown here on the left. We did this by using RNAi to impair the electron transport chain by feeding C. elegans bacteria expressing double-stranded RNA against coccyx-C, allowing them to grow to adulthood before testing our phenotypic, molecular and behavioural readouts on them. In addition, we used ISF1-CTV1, which is the mutation of the iron-sulfur protein in complex 3, as shown here, and this is an excellent proxy for chronic loss of electron transport chain activity. So I took both these approaches to addressing these questions, but in the interest of time today, I'm only going to be focusing on the work done with the acute depletion of the electron transport chain activity using coccyx-C RNAi. So firstly, I went ahead to confirm that reduced electron transport chain activity increases lifespan and stress resistance. We conducted lifespan by placing L1 worms following a bleach on either coccyx-C RNAi or empty vector L440. We allowed the worms to grow to day 1 of adulthood, where we transferred them every day until day 7, and thereafter we transferred them every 2 days. We scored the worms every day or every other day, and worms were marked as dead if there was no pharyngeal pumping or movement when picked with or touched with a platinum pick. And as you can see, there is a significant extension in these coccyx-C RNAi worms when compared to empty vector control, which shows that reduced electron transport chain activity promotes lifespan. So next we wanted to see if this was the same with stress resistance, which is a major proxy for proteostasis capacity. The difference between the two experiments was on day 3 of adulthood, there was an administration of a 35-degree heat shock for 4 hours to the worms, and then they were scored every day thereafter. And as you can see, there is a significant extension in stress resistance in the coccyx C RNAi condition when compared to empty vector control L0. Next, we wanted to see what happens to individual tissues when we impaired the electron transport chain. We measured muscle health by scoring the ability of the worm to move spontaneously or in response to touch. We found that there was a significant increase in muscle health or movement in the C. elegans which were exposed to coccyx C RNAi when compared to L040, showing that electron transport chain perturbation prolongs muscle function. In contrast, when we measured neuronal health as the ability of the worms to move towards an attractive odour, in this case benzaldehyde, we found that there was a slight reduction in coccyx C RNAi worms' ability to move towards the odorant, although this did not reach significant. We also found in this assay that both the coccyx C and L040 chemotaxis index declines from day 2 to day 9, showing that there is a decline in neuronal health when C. elegans age. Next, we wanted to measure the intestinal atrophy by measuring the worm's intestine posterior to the gonad relative to the worm's cross-sectional width. And we found that there was a significant increase in intestinal size between the coccyx C and the L040 on day 5 and day 8. However, by day 11, they had both atrophied to the same level. Next, or finally, we wanted to look at uterine health. We explored tumour growth in the uterus by measuring the tumour size posterior to the vulva relative to the worm's cross-sectional width. And we found that there was a significantly reduced tumour size on day 5, day 8 and day 11 in the coccyx C RNAi condition when compared to the empty vector control. So this shows that the electron transport chain perturbation throughout the whole organism increases stress resistance, lifespan, delays intestinal atrophy, prolongs muscle health, and suppresses tumour formation, whereas electron transport chain perturbation limits neuronal health. Next, we wanted to address question 2 and see which tissues the Mitochondria-to-HSF1 stress response works in order to enhance stress resistance, extend lifespan, and promote proteostasis. We performed RNAi in a tissue-specific manner and found that knocking down electron transport chain specifically in the neurons and the intestine extended lifespan. However, knocking down an electron transport chain in the muscle did not. Interestingly, however, when we tested stress resistance, we did not see an increase in stress resistance in the neurons or the intestine, showing it does not fit in with the enhanced proteostasis capacity as seen in the whole organism. To conclude, as mentioned earlier, mitochondrial stress in the whole organism leads to an increase in lifespan, stress resistance, muscle and intestinal health, reduced tumour growth, but having no impact on neuronal health. We also found that reduced electron transport chain in the neurons and the intestine leads to an increase in lifespan, but having no impact on stress resistance. But we found reduced electron transport chain in the muscle has no impact on lifespan or stress resistance. Future work will look into the impact that reducing the electron transport chain in germline has on stress resistance and lifespan also. These experiments are the first to reveal how reduced electron transport chain activity influences the health of different tissues in an aging animal, and which tissues the Mitochondria-to-HSF1 stress response operates in to extend lifespan, enhance stress resistance, and promote proteostasis and healthy aging, crucial when ascertaining whether broad activation of the Mitochondria-to-HSF1 stress response is a viable approach to promote healthy aging. I just wanted to thank John, Rihanna, Olivia, Maria and Yaya for all the support they've given me in the lab. I've thoroughly enjoyed being in the lab this year, as well as the GEMS lab and the Institute of Healthy Aging for their support, and Dr. Andrew Batchelor for the feedback and the support he's given me during the course. I hope you enjoyed my talk and any questions